Section 4.1 is titled Related Rates, and hopefully really soon we'll be able to figure out exactly what that is. One of the key things that we need to do in this section, though, is remember how to do implicit differentiation. So let's do a quick review of implicit differentiation. With implicit differentiation, what we were looking at was an equation that typically had a mixes of x's and y's, and we wanted to find the derivative of y with respect to x. So to give you an example, if we had something like x squared plus y cubed equals 5. Okay, if I wanted to find dy dx, we're treating y as a function and x as a variable. So when I differentiate x squared, x is my variable, so x squared is my function, and the derivative is 2x. When I look at y cubed, y is a function, which is then cubed, which is another function, so I'm thinking of y as being the inside function. So we use the chain rule, right? So I get 3 inside function, which is y squared, times the derivative of the inside function, and the derivative of y is just dy dx. Okay. So then I can solve for dy dx algebraically, right? So we just subtract 2x. So 3y squared dy dx equals negative 2x. And then I can go ahead and divide both sides by 3y squared. And we get that dy over dx is negative 2x over 3y squared. All right, I'm going to take this exact same equation, and I'm going to ask a different question. Find dy dt. Well, I don't see a t in here. What we need to know is maybe a little context, but oftentimes we can think of x as a function of t. Okay, and y is also a function of t, right? So when I look at this, x squared plus y cubed equals 5, both of these are functions of this third variable t. So when I differentiate, I'm using implicit differentiation, or the chain rule on both of these pieces when I do implicit differentiation. So the derivative of x squared is going to be 2x times the derivative of the inside stuff, and I'm taking the derivative of x with respect to t. Okay, when I differentiate y cubed, we get 3 inside functions squared times the derivative of the inside stuff. Okay, and then if we wanted to solve for dy dt, we could do that algebraically as usual. But what I want to point out here is that when we use implicit differentiation, the reason that we really wanted to emphasize Leibniz notation was because we might have the exact same function and pick different things to be my variable. Okay, and that's something that might come up more in 4.1 than maybe did back in 3.8. All right, so now let's go ahead and take a look at a related rates problem. So I'm going to start with an example. So let's suppose that we have two cars driving on different roads. Okay. All right, so one car is headed south and another car is headed west. Now let's suppose they start from the same point. Okay, so we'll say that car A is driving south and car B is driving west. And we'll give speeds for these cars. Okay. So let's say that car A is driving south, maybe at 50 miles an hour. And car B is driving west at 60 miles an hour. Okay, and we want to know how fast are the two cars driving apart. Okay, let's say after 2 hours. Okay, so I'm going to draw a diagram here. So on my diagram, we'll say that I have a starting point here, and car A is driving south, so going down this way, we'll say at some point we have car A here. Car B is driving west. Okay, and there is some distance between the two cars. So if I draw a line connecting them, the length of that line segment is going to be the distance between them. Okay, we'll call it D for distance. All right, when we ask how fast are the cars moving apart, what we're asking for is what is the rate of change of the distance between the cars. So our goal is to find the rate of change of distance with respect to time. So if distance is the function d, I want the derivative of d with respect to time t. Okay. Now car A is moving, so I can say the distance from car A to the starting point is a variable, and the distance from car B to the starting point is a variable. Okay. So let's just call those x and y. We didn't have to use x and y, though. You could have used, like, say, a and b or something like that. That would have worked fine, too. So I'm going to make a list of things that we know. And it's not very much, but it is something. We know how fast car A is moving, and since y is a distance between car A and the starting point, then the rate of change of y is going to be how fast car A is moving. So we know that the derivative of y with respect to time t is the speed of the car. So if I measure y in miles, then the derivative is going to be 50 miles per hour. Okay. Likewise, the rate of change of x is going to be the speed of car B. Notice that y is increasing over time, x is increasing over time, so I want to make sure that these derivatives are both positive numbers. All right, I want to find d dt, and I want to find that when my time t is 2 hours. Well, after 2 hours, I can figure out distances for x and y. I know that if car B has been traveling for 2 hours and it's traveling at 60 miles per hour, then the distance is going to be 2 times 60, or 120 miles. And similarly, if car A has been driving for 2 hours at 50 miles per hour, then the distance that it has traveled is 2 times 50, or 100 miles. Okay. Now I need to find an equation that involves this distance d and relates it to some of the information that I know. Okay, so if I look at what I have drawn, I have this triangle where the sides are the variables x, y, and d, and it is a right triangle. So we can use the Pythagorean theorem to get that x squared plus y squared equals d squared. Okay, x, y, and d are all changing over time, so all of these are functions of time t. So I can think of, when I do implicit differentiation, each one of these three as being functions. So when I differentiate, I'm going to get the 2 comes down, inside function stays the same, lower the power by 1, so that's to the power of 1, times the derivative of the inside stuff. The derivative of x is dx dt. When I differentiate y, same story. The 2 comes down, y, lower the power by 1, so it's y to the power of 1 times the derivative of the inside function. On the right-hand side, same thing. The 2 comes down, d to the 1 times the derivative of d with respect to time t. Okay, now that I'm done differentiating, if I want to, I can plug in, and my goal is to find d dt when t equals 2. And when t equals 2, I know all of this other information. Okay, so I'm going to go ahead and plug in. So x is 120, dx dt is 60, y is 100, dy dt is 50, but I don't know a value for d, and I don't know dd dt. dd dt is the thing I'm trying to find, so I'm still stuck with one equation and 2 variables, so I need more information. So going back to my original equation, x squared plus y squared equals d squared, if I plug in x is 120 and y is 100, then I can solve for d. Okay, so I have 120 squared plus 100 squared. When I add those up, I get 24,400. And then take a square root. So d is the square root of 24,400, which is approximately 156.205. Okay. So I can plug that in for d. So 2 times 120 times 60 gives me 14,400. Plus 2 times 100 times 50, which is 10,000, and then 2 times 156.205 gives me 312.41. Okay, so I can add and divide, and I get a value for dd dt. So this comes out to 78.105, or 103 rather, and the units would be in miles per hour. Okay, so a couple of comments here. One very important thing to recognize when we're taking, when we're finding these related rates problems is, I had this equation, and anything that's a variable, I leave a variable, and then I differentiate. If I plug in for x and I plug in for y, or maybe just one or the other, when I go to take a derivative, that's a constant, and so the derivative would be 0, so I'm not going to get the same answer. But thinking more conceptually, once I plug into a variable, I now have a number. Numbers don't change over time. So I'm telling my equation that that thing is not changing. So this is a very different problem if x isn't changing or if x and y aren't changing. If x and y aren't changing, then d won't change either. Okay, and so I'll just get 0. But that's not what we want to model. We want to model what's happening as the cars are moving. So we need to leave x and y as variables. So it's really important that anything that changes over time stays a variable until after you differentiate, and then you can plug in. Now we had to go back and find a value for d, so we went back to the original equation and solved for it. But we didn't use that as a fixed number when we differentiated. We left it as a variable when we differentiated. Okay, so that's important. The reason that we call this related rates is because what we ended up happening after we took a derivative was we had this equation that involved different rates of change. So it gives us relationships between different rates of change, hence the related rates. All right. What I want to do is go through another example now. And as I go through this example, I want to outline a process that we can use for breaking apart these related rates problems. Okay, so we'll have our example on the left, and we'll have our process or guidelines. Okay, and the reason I'm going to call these guidelines instead of these are the steps to solve the problem is because different problems work a little bit differently, and the guidelines won't always work the same. All right, so here's our problem. I'll type this out. Let's suppose that air is pumped into a balloon. We're going to assume that the balloon is a perfect sphere because we have a nice equation for that. Real balloons have kind of a weird oblong shape that would be a little bit more challenging to model, so we're just going to ignore that for now. Okay, so air is pumped into a spherical balloon so that its volume is increasing at a constant rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? The thing that I like to do as a first step when I'm doing a related rates problem is to draw a diagram. You could also say, like, read through the problem, but you don't need to be told to read the problem. But I like to draw a diagram. You could also call it a picture. I think that when I call what I draw a picture, that's insulting to pictures, so I call it a diagram because it doesn't look great. But the key is that I list out what the variables are and how they relate to each other. Okay, so you can see this very clearly in the last problem. Here is our diagram, and by labeling the variables, it was very easy to come up with an equation that related our variables. Okay. It was also easy to label where the different things like speed goes on what and things like that. Okay, so a diagram can help you keep your variables straight and also help you with finding an equation. All right, once we have so let's go ahead and draw a diagram then. For this problem, and here's an example of how the guidelines don't always work. If all I have going on is this spherical balloon, I don't really have a whole lot to draw. Also, when I draw a sphere, it looks a lot like a circle. We can maybe do something like that, put a little shiny spot on it. Maybe that looks like a sphere then, but I don't really think so. So when I draw a sphere on a page, it looks exactly like a circle, and we're just going to have to live with that and imagine the third dimension. Okay, the next step is going to be assign variables. Okay, so I know that the diameter of the balloon is how far it is across. We'll say D for diameter, R for radius. I can't really draw in a volume or anything like that, so there's not a whole lot more else, to draw. All right, so let's go on to our next step. So we want to express all the given information in terms of the variables that we have. Okay, in this case, I have radius, I labeled an R on here, I have diameter, I labeled a D on here. Okay, so let's look at what we were given. The first thing that we're given is volume is increasing. Anytime I see something like increasing, that should be an indicator that that's a rate of change, which is the derivative of something. Okay, so if I have volume V, then to say volume is increasing at some rate, that's the rate of change of volume. So that's dV dt. Okay, so dV dt is 100 cubic centimeters per second. And then it's asking how fast is the radius of the balloon increasing when the diameter is 50 centimeters. So I know that, at some point diameter is going to be equal to 50 centimeters. But I want to leave it as a variable until I'm done with the problem. Okay, after we express our given information, we also want to identify the goal. This is, I think, very helpful to prevent us from getting lost in the problem. So it says in the problem, how fast is the radius of the balloon increasing? So I want to find a rate of change of radius. So dr dt. By having that written down in front of me, even if it's easy to find in the problem, it makes it easier to make choices later when we're thinking about other things. Okay, next step, let's go ahead and find an equation. I'm not looking for an equation that has dr dt in it and dv dt in it. If I have these rates of change, I want to relate the variables that lie underneath them. So I want to relate the volume v and the radius r. We also have a diameter d in here, and maybe that'll come in handy, or maybe it's extraneous information. I don't know at this point, but I know that if I have a rate of change of volume and I want to find a rate of change of radius, I need an equation that involves volume and radius. Since this is a sphere, I'm going to use the equation for volume of a sphere. So we go and look that up, and we get 4/3 pi r cubed. So now that we have an equation, we can go ahead and use implicit differentiation. All right, so you're going to be using the chain rule on all of these pieces to take a derivative of your equation and get a bunch of rates of change. So when I take the derivative of v with respect to t, I get dv dt. 4/3 is a constant. Pi is a constant. When I differentiate r cubed, the 3 comes down, inside function stays the same, lower the power by 1, and then we multiply by the derivative of the inside function, dr dt. Our goal is to find dr dt, so I need to be able to plug in r and dv dt. I'm given dv dt, so I need to be able to plug in r, and that's where knowing the diameter is going to come in. Okay, so since d equals 50, r is going to be half that, or 25. So what did I do there? I needed to solve for one of the variables to be able to plug in. So our last step here is going to be plug in your variables. And what we want to do is solve for the missing rate of change. We may have to solve for a variable. So as part of that step, we might have something like this where we had the diameter and we use that to find the radius, because it's really the radius that we want to plug in. So now I'm going to go ahead and plug in dv dt is 100. We have 4/3 pi times 3 times 25 squared times dr dt. Okay. A little simplifying as we go, right? The 4 and the 3 cancel. Okay. So I can take 25 squared times 4, that's 2,500. So we have 100 divided by 2,500 pi equals dr dt. And we can leave it as a nice number like that, or if you want, we can divide that and get a decimal approximation. When I divide that out, I get 0.0127, and our units are going to be centimeters per second. Okay, so this is the process for related rates.